VSEPR, that seemed to be saying, I remember different shapes there, right? Don't you remember shapes as well? If we have 4 electron clouds around, to fill a full octet around an orbital, then there should be like 4 different, you should have 4 electrons that are trying to get maximally as far away from each other. Like what happened to that? That was just like last time. What happened there? So yeah, the problem, s orbital is spherical, right? The p orbitals are parallel to 3 axes, as we saw in those examples with a hydrogen sulfide and hydrogen selenide. But by CH4, by VSEPR theory, is tetrahedral. Now these are both approximations, but let's be consistent in these approximations. What's actually going on when we combine these orbitals? How do we get tetrahedral geometry from S and P? And so it turns out that when you look at possible new orbitals you can form out of combinations of S, Px, Py, Pz, you can come up with potentially new combinations of those orbitals that have different shapes. And so carbon has these 4 orbitals, but you can look at combinations of these orbitals to get new orbitals that actually do have a tetrahedral geometry. These are called hybrid orbitals. They're hybrid orbitals. They're combinations of the S and P orbitals. And we call these sp3. You have 3 identical, or you get these 4 non-identical orbitals and get 4 identical orbitals, 1 from S, 3 from P's, 4 orbitals that are each oriented at 109.5 degrees angles from each other. So, so these are combinations of the other orbitals. That's what they call hybrid orbitals. So hybrid orbitals for bonding with correct geometry, 1s and 3p orbitals, you get these 4 tetrahedral hybrids. You've got essentially 1 large positive node, 1 large positive lobe and 1 negative lobe. It still has that node because of the combination of the s's. And these do have the correct bonding for VSEPR geometry. And so, the solution is to this overall problem is when we combine the orbitals, we don't necessarily get just the orbitals that appear to be empty. We get combinations. You can lower the energy by combining to get new combinations of orbitals. And it's not entirely surprising that this combination of orbitals would end up being lower energy in certain circumstances because you're trying to get those electrons, further apart from each other. So what happens here? Let's start with a carbon in a ground state electron configuration. And you can imagine, getting carbon into an excited state configuration. And then once that's the case, so that they all have spin up and then combining them. And so we get carbon, we get 4 equivalent orbitals that are sp3 hybridized. And carbon very commonly very commonly hybridizes. Basically all of the first row of the main group elements, oxygen, nitrogen, they mostly hybridize. To come up with the other examples where it didn't hybridize, where it was just combinations of pure S or nearly pure S and nearly pure P, we had to go lower down the periodic table because those energy differences were larger. So reviewing the geometry again, you have Px, Py, Pz, and an S that combine to make the 4 tetrahedral orbitals that have those shapes. But there's other possibilities as well. There are cases where the lowest energy state might involve combining the S and just 2 of the P orbitals. So for example, if you have sp2 hybridization, then you would have combinations of, you have 1 p orbital that doesn't combine and 2 p that is not involved in bonding, and then at least not involved in sigma bonding, and that these orbitals are, these are 120 degrees apart, and that is sp2 bonding, and that is what you might get if there are, if the p orbital is not occupied, then you would get separation of 120 degrees. That looks, that is a lot more like sp2, like the trigonal planar geometry in VSEPR theory. So so that's another possibility, is combinations of the s orbital with only 2 of the p orbitals, and then obviously this, the interesting shapes are going to be in the plane because it's not using an orbital that goes that it goes up and down in the z direction. So what you generally see VSEPR, if it's linear, it's because you have sp hybridization. And there, you remember the sp bond is linear. And then for trigonal planar, you'd have S and 2p's to create 3 sp2 hybrids. There's 3 because there's 1 S and 2 p's, so there's 3 equivalent sp2 hybrids. A tetrahedral, you get 4 equivalent sp3 hybrids. And I'm actually going to stop here on this. The book talks a little bit about hybrids with d orbitals, but in the recent years, there have been some very careful quantum chemistry calculations, and it turns out that trigonal bipyramidal, and octahedral compounds, their orbitals are really not actually hybrids of sp3d. It's a more complex thing, and describing it as an sp3d hybrid is not actually very accurate. So I'm actually not going to quiz on that because it's even though the book talks about that, the most recent research indicates that these molecular orbitals are more complicated. They can't really be described as sp3d or sp3d2. It's a nice theory, but in the other cases, like in combinations of sp, sp2, sp3 hybrid orbitals, those are actually pretty good quantum mechanical descriptions of what's going on. But describing trigonal bipyramidal as being sp3d or octahedral as sp3d2 is actually not a very good description. So I'm not gonna, we're gonna ignore that part of the book because it's no longer a good approximation, unlike the other cases. So these hybrid orbitals forms single bonds in the molecular framework, but what about double bonds, right? Remember, most of the time when we had a trigonal planar molecule in a Lewis structure, the carbonate atom, there was always a double bond there, right? The carbon, it had to have a double bond if it was going to have 3 regions of electron density around the central atom and still have a complete octet, right? If you only got 3 bonds, you need either a lone pair or another bond in there to satisfy the octet rule. So let's see how they actually combined. So if we have, we'll get into that. Let's talk about how they actually form in terms of molecules. So hybridization sp3 orbitals. So if we have if we have a carbon, it can form these 4 carbon sp3 hybrid orbitals and combined with the 4 S1 orbitals, empty S1 orbitals of hydrogen, and combined to form 4 sigma bonds. Each of the 4 CH bonds results from the head-on overlap of a singly occupied carbon sp3 or hybrid orbital with a hydrogen 1s orbital. And now you have 4 identical orbitals that are each sharing 2 electrons. So in this case, the methane is this combination of 4 hybrid orbitals. What's the hybridization of the oxygen atom in H2O? Well, let's look at the Lewis structure. So the Lewis structure, remember, has OHH, and the total number of electrons, right, is 6 plus 2, 8 electrons. So we put 2 more lone pairs here. And so we have these 4 regions of electron density, but we also know that the angle of oxygen is about 107 degrees. And so this is going to be essentially, these electrons are in hybrid sp3 orbitals. And so because the geometry of water is sort of a bent molecule with sort of 2 butterfly wings of electrons there, this is sp3 hybridization. These sp3 orbitals are involved in the sigma bonds between the oxygen and the H. So there's a sigma bond here and a sigma bond here. And then the other 4 electrons are in the 2 unused sp3 orbitals. When you form the molecule, the lowest energy state is to form the hybrid sp3 orbitals that can combine with the hydrogens. But in order to form those orbitals, you end up putting the lone pairs into those sp3 orbitals. And that's why the lone pairs and the electron density is oriented like that. It's because those lone pairs are in sp3 orbitals.